Okay, so let's do an example because I think people are a little bit confused. So let's take a free particle, okay? So for a free particle, the Hamiltonian is just p squared by 2m. There's no potential energy term, right? In that case, my Schrodinger equation is I h bar d psi by dt is equal to minus h squared by 2m del squared of psi. Okay? So if I solve this equation, then I have psi of E for energy, is going to be equal to e to the power, some constant e to the power, minus I by h bar, say p dot x minus et. But here, what is the value? What is e? E here is given by p squared by 2m. Okay, so this is an eigenfunction of the Hamiltonian operator. What is the Hamiltonian operator? It's minus h squared by 2m del squared, right? So let's see if this is the case. So if I apply h to psi of e, what do I get? It's minus h squared by 2m. Here we have del squared. What is psi e is c times e to the power minus I by h bar, p dot x minus e dot t, right? So right, so this thing, what will it do? It's just going to bring down two factors of minus I over h. So it'll minus I h squared p squared c e to the power minus I h bar p dot x minus et, right? But this whole thing is just psi. So here we see that what we have is that h squared will cancel this h squared, and this I squared, it gives me a minus sign. That'll just get rid of this minus sign. So at the end of the day, I will get p squared by 2m psi of e. But what is this? This is nothing but the energy of the particle, right? So here we see that psi of e is a eigenstate. Eigenstate of the H operator, okay? Now, this is also an eigenstate. Psi e is also an eigenstate of, can you guess? Which other operator?
Momentum?
Okay, anybody else? Any other guesses? Right, it's a momentum operator. So if I act on psi of e by p, what is p? P is h bar by I. It's a gradient acting on psi of e. So psi of e has c, but that's a constant. It comes out. So I get e to the power minus I by h bar p dot x minus et. Then this just brings on one factor of I minus I h bar p. So we see that maybe just take plus here, it doesn't matter because we can play with the sign of p. And then what I get is, I get p times psi of e, right? But it is not, say, a, it's not an eigenstate of the position operator, right? So, yeah, you just get some Yeah. Although in this case, the position operator is just a, it's just a function, right? So you basically get a triviality. So there's no physical content to that. Okay. So any other? So I think let's stop here because I don't have any more. I haven't prepared more stuff, and I will have one more axiom to go through, which will be the collapse axiom in the next one, and then we'll go back to doing some more physical examples of quantum mechanical systems. Okay. Any questions? So, so when we say, okay, I'm doing the Fourier analysis of of a free particle, of a wave packet, what we are doing is we are saying AK and then square root of 2 pi h bar e to the power minus or plus h bar, sorry, I by h bar px minus et d cubed of k. These are the basis, these are the energy eigenstates, and these are the coefficients, like the CIs. Okay? So if I ask you, or I should really put a P here, if I ask you what is the, what is the the probability of having momentum value between, say, P and P plus, say, del of P, then what we'll have is that it'll be given by something like this, a squared of P d cubed of P. Okay. So what I want to say is that this equation is analogous to this equation. This equation. What we're doing in this equation is that we were taking some any old state and expanding them in terms of eigenfunctions of O. And here what we're doing is that we're taking essentially any old state and expanding them in terms of eigenfunctions of P. Okay, and this is just the time evolution of that eigenstate. And so these coefficients are analogous to the C coefficients that we saw. So, we'll set problems about this. So this will become more, it'll become much more, understandable. Okay, do you have any questions?